From the beautiful South Studios of Way Happy, this is Mr. Meyer and 5-1 transformation to quadratics. Now, what are quadratics? Quadratics are a fancy word for saying, hey, x squared is the biggest exponent you have in your problem, right? So right there is an x squared, and that's the biggest exponent I have. That means it's a quadratic. So that's a fancy way of saying what a quadratic is. And what do we need to know about quadratics? We need to know that quadratic graphs are always, I'm going to say U-shaped, but they're parabolas, right? They look like that. That's an x squared graph, where some kids confuse it with their good friend, the absolute value graph, that looks like a nice pointy straight lined V. These are actually curved a bit. So quadratics are curved, where absolute value graphs are nice and straight, but they share a lot of the same properties, so that's good to know. All right, so you know it's a parabola. You know it's got an x squared in it. Whenever you see an x squared in your problem, and that's the largest exponent, so it's not an x cubed or an x to the fourth, that's when you know you're talking about a quadratic, a parabola. So this says graph by using a table, and what a table is you making an XY chart like you did when you first learned to graph and plotting points. Now, it's not the best method because you could be plotting for a while, but it's not the worst method either. If I'm in trouble and I have no idea how to do something, I'm just going to make up some darn x's, and I'll make up x's that are easy, like 0. If I plug a 0 in for the x's, I get 0, 0, 3. I get 3. So I'm going to plot the point 0, 3, big old dot. Then I'm going to, try x is 1. Remember, these are my x's. I just did 0, 3. Now I'm going to do 1. So I'm like, all right, let's do 1. That would be 1. Let's see, what would we have? We'd have 1 minus 4 plus 3, which is negative 3 plus 3, which is 0. So we'd have the point 1, 0. So boom, there's 1, 0. Now I'm going to try x is 2 and see where the graph goes. So I'm going to try 2, and you can see this could take a while. So I plug in a 2, I would get 2 squared is 4 minus 8 plus 3. What's that? Negative 4 plus 3. I think that's negative 1. So right here, it's negative 1. All right. It's starting to look like it's curving. That's good. Otherwise, I was going to go try some negative x's, but I'm now going to stick with my positive x's. I'm going to try 3. And if I plug in 3, I get 9 minus 12 plus 3. What is that? 9 minus 12 is negative 3 plus 3 is 0 again. So now I have 3, 0. And there you can kind of see the bottom of the parabola. Parabolas are either going to have, a top or a bottom, what we call a maximum or a minimum. And this definitely looks to have a minimum value. If you want to make sure, you could plug in a 4, and you could be like, all right, that's 16 minus 16 plus 3, or that's going to be 3. So 4 is going to be right here again. And you can see this beautiful parabola must look something like this. Now, there's a lot of cool things that we need to talk about on a parabola, like this point right here, this minimum point. We call that the vertex. That is the most important point, really, because the vertex has what's called a line of symmetry that goes through it. So some books call this an axis of symmetry. Some call it a line of symmetry. And all that means is that you are equal. Every point on the parabola is equal distant on the left and the right of the line of symmetry. So once you know where a line of symmetry is, technically you could just plot some points and on one side and then just kind of copy them over to the other side if you have the correct line of symmetry. So that's what we call a line of symmetry. That's what we call a vertex. That's what we call a parabola. Let's have some fun. They want to move these things around. So how do you move graphs? First off, let's do the easy one, the vertical translation on this side. The vertical translations are how you move stuff up and down. So if you take a parabola, here's a parabola. That's the most generic parabola I can think of, right? If you take that parabola and you just add something to the back of it, plus 4, you just move the parabola up 4. That's what all this stuff is saying, right? If you add something to the entire graph, remember, this is the parent function. This is the parabola. That's the graph. If you add it to the entire graph, you have just moved that graph up. And if you're going to subtract, you're going to move it down. So if I wanted to move the parabola down 4, I would just take x squared and I would put minus 4 on the back. That would take that entire parabola and it would move it down 4. Now, those were the easy ones, right? Remember, vertical ones are always the fun, easy ones. What about the horizontal ones on this side? Right? These guys over here, they're not as easy because you have to do it to the x. And when you do the horizontal ones, you got to think opposites. So here's the parabola again. We'll call it x squared. But now say I want to move it left. Then what I got to do is I got to come in here and I got to go just to the x, right? So it's still x squared now, but I'm going to move, now I'm going to attach just to the x. I wanted to go left, so I'm going to go the opposite, which is +2. Now notice that's weird. You would think plus would move it right when you're talking left and rights, but because it's inside happening to the x, or because it's horizontal, it's odd. And so you do the opposite of what it is. And so this would be a left 2 shift. So you have to be able to recognize when it is a horizontal left and right, or when it is up and down. And you can tell pretty easily once you get used to it. If it is happening just to the x value, that's going to be a left or right shift. And if it's happening to the entire x squared, that's going to be up and down. All right, let's see. Here's example 2. You tell me the shifts, and look at that. They threw both of the shifts at the same time. They said, here's your x squared graph. Now, what did this do, and what did this do to your x squared graph? Well, I can see the -2 in here. This is going to be what we call a right 2 shift. And this is going to be an up 4 shift. That's right. Right. So that means that that's how you would move a parabola. So instead of having this, here's the parent function, right? It would have this dot, the vertex right here, and then have a arm going up on the left, an arm going up on the right. Well, what we've just done is we've moved it. I'll do it here in green. We've moved it right 2 and up 4. So now that dot is right here at right 2 up and 4. The vertex is actually moved, and the parabola is going up on this side and up on this side. So I've actually moved that entire parabola right 2 and up 4 just by moving the vertex. How beautiful is that? And you could have figured that out, by making an XY chart or something like that. Maybe plotting one other point. Now let's look at this one again. Something happening to the x that is horizontal, left and right. You got to think opposite. So +2 is actually the opposite direction, or what I will call left 2. And then something added to the entire function, the x squared function, is getting a -3 on it. That's going to move it down 3. And so when I graph this bad boy, I'm going to go left 2. I'm going to go down 3. And then I'm going to put my magic dot, my vertex, and I'm going to go up and to the right and up and to the left, and you have a graph. Now, if somebody wants a really pretty graph, I'm going to make a little XY chart for them to have like a bunch of points. Maybe I want to get 5 points on the parabola. That would always be a good idea, is to plot 5 points, right? And which points would I pick? Well, look, the first point I would pick is left 2, down 3. Left 2, down 3. I know that point is on there because I'm the one that put the vertex on there. Then I'd pick things like -3 and -4 on one side, the lower side, right? And then if I want to go higher, -1 and 0, I would pick things on either side of the vertex. They should come up with kind of similar answers because it's a parabola and that whole thing called the line of symmetry. Nice. Let me ask you a question and I'll be right back. All right, nice work on that one. All right, what about the next part now? How do we reflect these things, or, make them open down, right? Well, the big trick is not so tricky there. You can see that all right here. If you take a graph, so again, here's our x squared graph, and I'm going to take the most simple of all, just this regular old parabola. If I decide that I'm going to do the first box this time, if I want to reflect it across the y-axis, then all I'm going to do is take that x, and I'm going to make it negative. And then the squaring happens. And that right there will reflect the graph across the y-axis. Now look at the graph over there. It's kind of silly, right? If you were to reflect it over the y-axis, then the right arm would become the left arm, the left arm would become the right arm, and wait a minute, it would look exactly the same. So a y-axis reflection is kind of weird on parabolas because doesn't actually happen. Remember what happens when you square a negative number? You get the positive number back. So in fact, if I finish doing the algebra here, if I squared this negative number, I would still have x squared. And that was the original graph. So it looks just like its parent. So when you put a negative on the x, it doesn't do too much to the graph. Now it could mess up the translations. So don't let you think it's always just disappears. It doesn't. There's times where you have to factor out a -1 so you can read the correct left and right translation. So be worried about that. Now, how do you make it reflect over the x-axis? This guy right here, you just take your regular old graph, but you drop a negative out front of that graph. So you take the graph that you had and you put a negative out front. So notice no parentheses this time, right? So this means you have to square first and then you make your answer negative. It should be almost written like -1 times x squared. That would probably look better because that would make people understand, oh, you square first and you do -1 times that after. So that is not such a big deal, but make sure that you understand what kind of transformation that is. That is called a reflection. All right, so there's a reflecting across the y, reflecting on the x. If I have that vertical reflection, that's going to make it open down. All right, now the super confusing ones, the stretches and compresses, right? So the horizontal one, remember, is always the opposite. So again, I'll start on the left side. If I'm going to do a horizontal compression, then what that means is I'm going to take the graph and I'm going to either stretch it out or I'm going to compress it. But horizontally means you have to do it just to the x, right? So I'm going to put a number in here with the x. Now look, if that number is bigger than 1, that means you stretch it, and if it's smaller than 1, you compress it. But horizontals are odd, and you always got to do it a weird way. So in fact, multiplying this by 4 is actually a compression. What? This is going to be a horizontal compression of 4, or 1/4 if you want to know what the factor is, right? So you would compress this thing horizontally by a factor of 1/4. It would get skinnier, is what you want to think of. It gets compressed horizontally, left to right. It is getting smushed together from the sides, and that would make it a skinnier graph. Now, if you multiply by a fraction, if I would have put a 1/3 in there, that would be a horizontal stretch. So y equals, 1/3 x squared. That, again, horizontal means the opposite. So flip that in your brain and call that a 3 and go, oh, it's a stretch. So in your brain, you always got to think of a horizontal one being opposite. And so that is an opposite. So that is a stretch of 3. So this is a horizontal stretch. It would make the graph wider, pulling it left and right, making it fatter. All right, what about if you were going to do this to the vertical one, the easy one, the one I don't have to do opposites of? Well, it is just that. Here's the original, right? If I want to stretch it, I multiply it by a number bigger than 1. 7x squared is going to be vertically stretched. I took x squared and I multiplied it by 7. That makes the graph tall and skinny, right? It stretches it vertically. It like takes your head and pulls it up, right? So that's what it would do if you were Gumby, of course. If I want to do a compression, I'll write vertical stretch. If I want to compress you vertically, I want to smush you down, then, in this case, a graph, I would take my graph, x squared, and I would multiply it by a fraction, something smaller than 1, like 3/4, right? That's smaller than 1. That would compress you vertically. So this is a vertical compression. And there you have your stretches. Now, when you graph, well, we'll talk about it after, but stretching before you slide. So here you go. Here's all your vertical stretches, your vertical compressions, and your flips. So now look, if I look at this and I want you to tell me what's going on, you see the x squared graph, and you notice there's a negative out front, which means that is a flip over the x-axis. So we'll call that a reflection over the x-axis. So it opens down now. It's parabola that opens down. And then I see the 1/4. Now that is not in there with the x, even though you're like, wait, it looks like it, but it's not. It's the x squared is going to happen first. The function will happen first, and then we'll multiply by the 1/4. So that's vertical. So this is a vertical shrink of 1/4, right? So it's smushing it down by 1/4. If you wanted to know what that graph would look like, you would take your graph paper like this, and you would have your vertex here because it's not moved. There's nothing added to the x or added to the back. And it opens down now, and it's vertically shrunk. So it's a little wider, right? Instead of being like this, somebody pushed it down this way. And so it kind of fattened out like this, but it got vertically stretched. Now, how could you always test? You could always test an XY point. Let x be a 1 and see what you get. And you could actually graph a point and be like, all right, I know exactly how it looks. All right, what about example B? It says the 3 is on the inside there. So remember, when it's on the inside, you got to think opposite. You got to think weird. So this is horizontal, but it's not a stretch. It's a compression, because in my brain, I have to be thinking of 1/3. So this is a horizontal compression, right? It is compressed to a third of what it was. So, or it's compressed by a factor of 3, if you like. So it's still a parabola that would open up normally like this, but now we've compressed it and we've made it, 1/3 as big. So if I plug in x is 1, I'd get y is 9. So instead of x being 1, 1 like it normally was, now I get 1, I get 9 is way up here. And you see that this guy has been compressed horizontally. He's been pushed in, right? These arms have been pushed in from where they were. So that is a horizontal compression of 1/3. All right, let me see what else I got here, if anything. There it is. It's called vertex form. Vertex form then is pretty much what you've just learned, right? It's y equals some number indicates which way it opens, up or down. X tells you where the vertex is, and H tells you where the vertex is. The opposite of H and K will tell you the vertex location. So this last melon right here, I want to describe a parent function x squared. I want to stretch it vertically by a factor of 4/3, translate it 2 left and 5 down, and create equation G. So G of x is going to be an x squared graph. But wait, I want to first do a stretch of 4/3. So I'm going to just multiply it by 4/3. That goes out front because it was vertical and it doesn't have to do anything weird. All right, now we do the translations. You're like, oh, wait, we want to move it 2 left. So that means we have to take this x out and we have to put that in. So that'd be 4/3, and then 2 left would be x plus 2. Remember opposites. And now you have moved that thing. You've not only vertically stretched it, but you've also moved it left too. And then the last melon, the last step is move it 5 down. Oh, that's simple. I am just going to take the 5 down. I'm going to take the graph that we have, and I'm going to throw a -5 on the back. And that is your G of x. That is your transformed one. It has a vertex of -2, -5. That's the vertex, right? And it opens up because it's positive out front. This means opens up. And it's vertically stretched a little bit. So instead of a normal parabola, it's stretched slightly. No biggie to me. That's it. Let me ask you a question. Have a great day, and I'll see you tomorrow.